Hello everyone, my name is Takayuki Tanabe. Welcome to my presentation. Today, I introduce a paper, an analysis of concurrency control protocols for in-memory databases with CCBench. This work was my master's research at the University of Tsukuba. This is our motivation. Current research tends to evaluate only scalability and rarely discusses other factors. Also, some researchers conduct evaluations using multiple platforms. Different platforms use different modules with different architectures, and the codes have some variations. In such a situation, performance depends on engineering efforts, so it compromises the fairness of the evaluation. So we developed a new analysis platform, CCBench. This is the architecture of CCBench. As shown, CCBench shares many modules for fair comparisons. I first explain shared objects. We unify data access method into mastery. The system forms a transactional key value store. Record formats in all protocols have a common structure such as memory placement. Metadata is adjacent to its payload in a record. CCBench tries to reduce memory allocation cost. Pre-allocation can be performed to reduce version allocation for MVCC. We also use the same workload generator and local read-write set structure. CCBench has 7 optimizations: decentralized ordering, invisible reads, no wait or wait, adaptive backup, read files extension, assertive version reuse, and rapid GC. ORG means originally proposed. CCB means newly implemented by CCBench. As you can see from the table, we apply optimizations even though it wasn't applied in the original paper. This is because we had an interest in fair evaluation. CCBench allows you to configure these optimizations and conduct detailed analysis on your purpose. We found they can be classified into 3 categories: cache, delay, and version lifetime. I explain these insights later. This is the experimental environment. We used 224 threads in all experiments except for the reproduction. We used YCSB benchmark. We used 5 workload parameters: skew, cardinality, payload, transaction size, and read ratio. The extended version in the archive also describes the TPCC. First, I review the importance of decentralized ordering. Centralized counter results in significant performance degradation. This is a read-only workload, and the horizontal axis shows the number of records. Protocols using decentralized ordering show novel performance, while protocols using centralized counter is less efficient because centralized counter axes are serialized with cache line conflict. Here I explain invisible reads. This is a transactional read operation that doesn't update the metadata. Invisible reads are cache-friendly because they reduce the right to share data, which causes cache replacement. The disadvantage is that using invisible reads, protocols can track anti-dependency. Siro has the property of invisible reads. TikTok doesn't have the property. We conducted an experiment focusing on cache between these protocols. We compared Siro and TikTok. This is the difference between invisible read and non-invisible read. Level 1K means a table size of 1,000 records. Level 1M means 1 million records. The horizontal axis is the read ratio. The vertical axis is throughput and cache miss ratio. Please see the left figure for throughput. When read ratio is less than 80%, TikTok 1K wins Siro 1K. This is because of the metadata update for anti-dependency tracking of TikTok. It works well in light-intensive workloads. Then please see the right figure for the cache miss ratio. We see more cache misses for TikTok 1K compared to Siro 1K. This is because of the invisible reads of silo or metadata update of TikTok. We can see almost the same cache miss ratio for silo 1M and TikTok 1M. However, silo 1M shows higher throughput than TikTok 1M. This is because TikTok does some extra computation compared to silo. Next, I explain delay control and extra reads. Delay control is efficient for highly contained workloads. No wait and adaptive backup optimizations are examples of explicit delays. On the other hand, the extra read is an example of implicit delay. Extra reads occur in the read phase of optimistic protocols. It is a repeated trial of read operation in order to read a record atomically, so it avoids dirty read. We compare silo and TikTok. As you can see in figure A, area board of TikTok works well in highly contained workload, which is small payload cases. Silo without area board optimization underperforms TikTok. From figure A and B, there is a correlation between throughput and extra reads, which suggests extra reads improves performance. Less extra reads in silo is because of the lack of area boards. That is, delay plays a key role. Interestingly, figure C shows that some artificial sleep provides high performance. We say this is a read phase extension, and its graph is similar to extra read. As shown in figure A, area board is effective. If you C, silo plus no ways, that means silo with area boards also shows novel performance. Thus, one can explore novel optimization methods that performs both. MVCC needs to hold multiple versions and tends to have many versions. Even if there is only one long transaction, it increases the number of versions that cannot be corrected by GC, even if it is a modern system like Rapid GC. This is an experiment with version lifetime. We use Kera that has Rapid GC. In this experiment, only a single worker processes long transactions and all the other processes short transactions. The level of figure indicates the artificial delay in the long transactions. We found a strong correlation between the delay of long transactions and the GC interval. The performances are limited by GC intervals. This is because even one long transaction prevents the progress of the GC. One needs to reduce visible versions to solve this problem. Conclusion: CCBench is a platform for fair comparison of concurrency control protocols. We found 3 key factors from experiment with 224 threads. CCBench source code and the experimental data are available online. Thank you for listening to our talk.